This afternoon we have the pleasure to start with a talk by Chris Ferro. The floor is yours.
Thank you. Good afternoon, everyone. And I'm very grateful to the organisers to have this chance to present this work, which is joint work with Tom Wilkinson, who's studying for a PhD with me. And he's in the audience. And I should say, I've underlined my name just because I'm the one who's standing up here, but Tom is the one who did all of the hard work. So please, I hope you get to speak to him as well at some point. This work is about multi-horizon predictions, and I should explain what I mean by that first. So this is where predictions are updated, and a familiar example is weather forecasts. So if we're interested in what will be the weather on Saturday, then the Met Office has made a forecast already for what Saturday's weather will be. But if you look tomorrow, they will have changed the forecast. It will be updated. And then if you look on Thursday, there will be a new forecast for Saturday. Friday, it will be updated again. So you've got this sequence of forecasts for the same outcome, the weather on Saturday, that you've got these updated forecasts. And what I want to discuss is how we might use these sequences of forecasts to assess the calibration of these forecasts. I first got interested in this idea of multi-horizon forecasts speaking to David Richardson, who used to be the head of the verification group at the European Centre for Medium Range Weather Forecasting in Reading, one of the leading weather forecasting centres in the world. And he'd retired a couple of years ago. But they were very concerned because they made their very good forecasts, but their customers didn't like it when the forecasts jumped. So maybe today's forecast for Saturday's weather is that it's raining, and then tomorrow maybe the forecast changes to say there's no rain, and then Thursday it changes again to say there's rain again. So the forecast is jumping when it gets updated, and the customers didn't like this. So the European Centre thought quite a lot about how do we know if these are good jumps in our forecasts. And they started to monitor this carefully and looking in great detail when the forecasts made some unusual jumps to try to understand why forecasts jumped in those ways. They even made a measure to monitor the jumpiness of the forecasts. They called it the flip-flop index. So it was sort of flipping from one thing to the next. So David asked me, how do we tell if the changes in our forecasts are good or not? I didn't think about that for a while, but then I learned that actually, particularly in the economics literature, these multi-horizon forecasts are looked at a lot, and there are ideas going back a few decades about good and bad jumps. Well, in that economics literature, then it's focused mainly on point forecasts, so jumps in point forecasts. But what we're going to discuss today is extending those ideas to probability forecasts. So the sorts of questions we're interested in, when the forecasts change, when they're revised, so I will go through revisions of forecasts, that's the changes in the forecasts. Are these changes appropriate? And if we analyse the revisions, what can that tell us about calibration? In the economics literature, they're often referred to the efficiency of forecasts, which is a sort of strong form of calibration. So this word efficiency is being used in a few different ways in this meeting, but I'll define what we mean in a moment. So yes, what will we do? We'll review what is meant by efficiency and revisions of point forecasts. then we'll extend that to probability forecasts and analyze what happens there. And yes, Tom has a poster on this where I'll give some mathematical detail in a rather informal way. And if you want more detailed theory, then please speak to Tom and look at his poster, which is just outside the door. So point forecasts, first of all, just reviewing what exists already in the literature. So there is an outcome, y, that we want to forecast. Maybe that's Saturday's weather. Although I'll consider just scalar valued outcome here. Then we have a probability forecast, and I'll denote that by f, representing the cumulative distribution function of the forecast. The forecasts are based on some information, which I'll denote by I. And then for point forecasts, this would usually, often be constructed as some functional of the probability forecast. So it might be the mean of the forecast distribution, or the median of the forecast distribution, or something else. And now we're going back to one of the first papers to discuss these ideas in the economics literature, so by Nordhaus in 1987. And he defined the point forecast X to be efficient if it equals the expectation of the outcome given the information that you're using. So this expectation is the true distribution of y given I. One could define, so here the point forecast X is like the mean of your forecast distribution. You could define this efficiency in more general ways, which connects with ideas of T-calibration, for example. And Johannes Resen is at this meeting as well, so you could ask him more about that if you wish. Also, another of my PhD students, Heba Basheik, discussed these ideas also in her PhD thesis, but I think the idea there has basically been around for quite a few years. However, yes, for us, point forecasts are efficient if the point forecast X equals the expected value of the outcome given the information that you're using. So now let's talk about multi-horizon forecasts. So we've got now a sequence of forecasts. Here they are, X1, X2, up to X8, for the same outcome, Y. And then a forecast revision is the change from one forecast to another, so from X1 to X2, or any other pair of forecasts. Just briefly to discuss why might we, I think we often don't analyze revisions of forecasts. We tend, not always by any means, but we maybe tend to fix a lead time and see how good are the forecasts at that lead time. But we can also analyze these revisions. And one of the main reasons given for why we might want to analyze revisions is that we don't then need to look at the outcome. Or at least when we analyze the revisions, we don't look at the outcome. And this can be useful in situations where maybe you don't know what the outcome is, or at least there's some uncertainty about it. For example, in financial forecasting, you might be trying to forecast volatility, which is not something that you observe directly. You have to estimate it. So there's some uncertainty there. Or in economic forecasting, you might be predicting GDP or something else like that. But estimates of GDP will get updated over time as well. So even you get a sort of first guess of what Y is, but then it'll only be a few months later that you get a better estimate of what Y is. And maybe there are even situations where you're making many forecasts, updating your forecasts, and you don't yet have any outcomes that you're trying to predict. And you might want to be able to say something about, is my forecasting system behaving in sensible ways? So that's one reason for thinking about analyzing revisions. And then we can also learn answer this question of David Richardson's: are our forecasts changing in appropriate ways? Are they jumping in the right way? And it also helps us, it sort of gives us another way of looking at calibration. Instead of just looking at fixed lead times, we can look at how the forecasts are changing. And that might help to explain why our forecasts are good or bad in certain ways. Maybe our forecasts are pretty well calibrated, but then at a certain lead time, we update in a bad way for some reason. And maybe this can help to understand in what way that update is bad. So, there are some reasons. Okay, so here is the main result that Nordhaus had. So here's our notation. x1 up to xn are point forecasts for the outcome y. They're issued through time. They're based on different information sets, I1 up to In. And crucially, I should probably have put this in as part of the proposition here, the information sets are nested. So I2 contains at least as much information as I1. So you don't forget some information as you go through time. And you maybe accumulate more information. So this is a crucial part of this. Here's our definition of efficiency. And this very nice result by Nordhaus is that if these point forecasts are efficient, then they form a martingale. And what that means is that the expected value of a future point forecast xj, given some previous point forecasts, x1 up to xi, is just the latest of these forecasts, xi. For those interested, I'd sort of give an outline of how you might prove this here. I'll just talk through this briefly for this case. Other proofs are kind of similar. So if we think about this conditional expectation, then the first equality just uses the assumption that xj is efficient. So here's xj. Then, because the information sets are nested, we can use the Tower property of expectation, and you get this, and then this is just the fact that xi is efficient as well. So you get this nice martingale property. What does it mean in practice, or what's the interpretation of this? Well, one way to think about it is that if the forecasts are not efficient, that would mean that our expectation for the future forecast xj would be different from our current forecast xi. But if we already expect that our future forecast is going to be different, then we should change our current forecast to be that thing. And so when we make that change, then our forecasts become efficient. So we can't sort of predict what our future forecast changes will be. So yeah, this martingale idea is the basis of all the results here. And you can test this martingale property. So you've got your sequence of forecasts, and there are various tests in the literature for testing this sort of martingale behavior here. You can also look then at the revisions. So previously that was for the point forecasts themselves, but now let's think about the revisions. So that's the changes in the forecast. So the revision from xi to xj is just their difference here. And here are the consequences of the martingale property that we had before. So these revisions form a martingale difference sequence. And so if the forecasts are efficient, then the revisions have mean 0. Their expectation is 0. And if the revision periods don't overlap, then the revisions are also uncorrelated. And so you can also analyze the revisions to check these properties empirically, given some data, given some forecasts. And then another consequence of this martingale property here is that the variances of the forecasts increase as you increase the revision period. And Patton and Timmerman proposed a test for this monotonicity of these variances as well. So this is the idea. You have, if the forecasts are efficient, then they have a nice martingale property. That has some consequences for the behavior of the revisions, and you can then test these properties empirically with some data, the forecasts, when you get them. I'm not going to talk about the statistical tests that we might use here. Okay, so some examples. And this is effectively very similar to the example that Nordhaus has in his nice short paper. So here we construct the outcome, y, and it's the end point of a random walk. So there are some z's, which are IID standard normal, and you add them all up, and that gives you the outcome. So the outcome is some end point out here. And then we're going to have a sequence of forecasts for this outcome. And we're going to get one forecast at each time. I is 1 up to n. And here are some very good forecasts, good point forecasts. So we get Z1, that's our first bit of information, and we let our first forecast X1 just be Z1. Then we get the next bit of information, Z2, and we update our forecast to get X2 by adding that Z in as well. And these are the best forecasts that you can make, and if this is really the process creating Y. And this is what the forecasts look like. So we see that really good forecasts do jump around. The ECMWF customers might not be very happy here, because it's jumping up, down. Nonetheless, these are the best forecasts we could be making in this situation. And so here we see some of the properties of the revisions. Okay, so in this case, the revisions are just these independent Zs, and they are indeed uncorrelated, and they've got mean 0. What about forecasts that are not efficient? So here's Nordhaus's example of that. So these forecasts are different now. So x1 is 1 minus alpha times z1. So it's not using all of z1, it's just uses a bit of z1. x2 is 1 minus alpha squared times z1 plus 1 minus alpha times z2. So it's using a bit more of z1. Alpha is between 0 and 1. So 1 minus alpha squared is a bit nearer to 1, but it's still not using all of z2. So the z's sort of get incorporated slowly over time. You add a bit more in each time. And that's the red line here, this slower moving one. So yeah, you're not incorporating the information efficiently. You're not putting it all in when you should do. And so, yeah, I call this under-responsive. It's under-responsive to new information. And there you find the revisions follow this autoregressive structure, and so the consecutive revisions are correlated now, instead of being uncorrelated. You can also, if you let alpha be negative here, you get this sort of behavior, which is a bit like the forecasts reacting too much to the new z's. You're adding in too much of each z as it comes along. That you've got the same sort of structure here. So these are some ways where point forecasts could be inefficient. All right, so that's point forecasts. And to my surprise, at least as far as I managed to find out, these ideas had not been extended fully to probability forecasts before. And so that's what Tom has been looking at. So let's talk about probability forecasts now. So first I need to define what we mean by good probability forecast. Same notation as before. Here's a forecast for an outcome, some information set I. And the definition of a good forecast that we want to use, it's already in the literature. So we say that F is ideal relative to the information set I if F is the distribution of Y given that information. Just to match with the first half of the talk, I'll refer to this as F being efficient. But yeah, it's maybe more commonly called ideal or optimal or some other words. And this is quite a strong requirement. For example, it implies auto-calibration, which is where you just condition on the forecast itself here, whereas here you might be conditioning on more information than just F. But yeah, that's what we mean by F being efficient. So now let's think about sequence of probability forecasts. So again, a single outcome, and we've got this sequence of forecasts being updated over time. The information on which they're based, again, is nested. Here's our definition of efficiency. And so here's our first result, is just like point forecasts, these CDFs, well, if they're efficient, then they also form a martingale in this sense, that the expected value of future forecast Fj is equal, given some earlier forecasts, is equal to the most recent forecast Fi. Proof is basically, well, here, this outline is basically the same as before. And the interpretation is the same as before. So if our expectation for our future forecast is different from our current forecast, then we should already change our current forecast to match that future expectation. And just to point out, since we've been talking about different types of calibration this week, so yeah, this efficiency requirement is quite strong, and this nested information sets here. So if your Fs are just individually auto-calibrated, which is what one might be trying to test, then this would not be strong enough necessarily for this martingale property to hold. You need to be conditioning on all of the previous forecasts here to have this martingale property. But now that we have this martingale property, we can then see what about revisions of probability forecasts. And the key step here for us was realizing how to define a revision of a probability forecast. This wasn't obvious. We tried a couple of things. But it turns out that a good thing to use is this. So we're revising the forecast from Fi to Fj, and we define the revision to be this function, Fj composed with Fi inverse. So R is some probability between 0 and 1. You find the R quantile of Fi, and then you see what probability point that is in the distribution Fj. If Fi equals Fj, for example, if the two forecasts are the same, then the revision is just the identity function. If you define revisions in this way, then you get these nice properties again, just like we had for the point forecasts. So if the forecasts are efficient, then the expected value of this revision function is the identity function, and the revisions are uncorrelated for any R and R prime if the revision periods don't overlap. And also you have this monotonicity of variances. We're sort of more interested in these ones, I think. So, yeah, we should maybe think about, all right, so we could, if you're given a sequence of forecasts, F1, F2, up to Fn, you can make these revisions, and then you could ask, okay, you could then ask about this sort of expectation here. If the forecasts are not efficient, then the expectation will not be the identity function. So if they're efficient, the expectation would lie on this diagonal. If they're inefficient, then you might get this expectation not lying on the diagonal. And we expect that different types of inefficiency could combine to give all sorts of patterns here. But here are some sort of the most, I think, basic ways in which the forecasts could go wrong. So one is just that if the forecast means, so those point forecasts, if they change in some systematic way, so if they tend to drift over time, then you would see this sort of behavior in the expected revision function. Either it would be above the diagonal or below the diagonal. Another thing that can go wrong is that the forecast variances have to change in such a way that they balance out the variability in the changes in the forecast means. And if they don't, then you get these sorts of sigmoid type behaviors here. So these are the sorts of things that this revision function might help you to diagnose if your forecasts are not behaving efficiently. We can have a look at our examples again. So this is the situation we had before. The outcome is the endpoint of a random walk. Now I have to make probability forecasts. So Fi is going to be a normal distribution with mean equal to this point forecast that we had before. This is the case of sort of the best forecast we could make. And here is the correct variance to use, explaining the variability in the remaining z's that we haven't observed yet. And so if you have, well, so that's what the sequence of efficient forecasts looks like. The means are what we had before, and then here's just plus or minus 1 standard deviation on the predicted distributions. So we see that the forecast variance is declining over time. And so we could then work out the revisions. We could work out the expected one-step revision, and you can show without too much effort that this does indeed give you the identity function. So these revisions satisfy this property here, and also the revisions are uncorrelated here as well. What happens if we don't have efficient probability forecasts? So here was one of the cases we had before. I've just changed the forecast means to be this under-responsive forecast means, the red curve here. So they're updating sort of too slowly in some sense. But I've kept the forecast variance the same. And what you can show here, for example, is that the final revision in the sequence, its expectation is approximately this. And this is not the identity function. And this corresponds to one of the patterns I showed earlier. And the interpretation is that these forecast variances, n minus I, they are reducing too much relative to your slowly changing forecast means. So for your forecasts to be efficient, if your means are changing this slowly, then your variances should not be reducing so much. But the real problem here is with the forecast means. They're updating too slowly. Here's another example we haven't seen before. And the point of this example is to show that here's a case where the point forecasts are perfect. These are the ideal point forecasts. So if we were just analyzing the point forecasts, we wouldn't be able to detect any problem. The forecast would look great. But here I've made the variances, the forecast variances, incorrect. They're too small. But more importantly here for the revisions is that they update, they reduce too slowly. And you can show here in this case that the expected revisions have this form. Again, this is not the identity function. And yeah, the interpretation, it's sort of the opposite to the previous slide, that these variances are reducing too little. So that the variances are too small, but it's the rate of change of these variances that's the problem. As far as the revisions are concerned, they're reducing too little. So these are some examples of what goes on when you examine forecast revisions. Just close this, this topic by noting a connection to probabilistic calibration, which has been mentioned previously this week. So this result was mentioned yesterday. We're thinking now of forecasts F1 to Fn, but they're forecasts for different outcomes, maybe a fixed lead time. So F1 is a forecast for Y1, Fn is a forecast for Yn. Again, information sets are nested here. And then there are these probability integral transform values, pit values, which are defined in this way. And yes, well, if you're working with continuous quantities, things are defined in this way. And there's a generalization where when you're working with discrete distributions. But there's this result from Diebold et al. That if these nested information sets also include earlier outcomes, earlier Ys, then if these forecasts are efficient, in the same sense that we had previously, then these pit values are not only uniformly distributed, but they're also independent. And okay, well, I've mentioned the proof, which is essentially what they have. And there's a strong similarity between this result and what we had with our martingale result for revisions of probability forecasts. And that's what I'll show on the next slide. What I'll show on the next slide is that we can define quantities equivalent to these pit values. We call them synthetic pit values, which under efficiency have the same independent uniform behavior. But because they're based just on revisions, they don't use the outcomes Y, and so we don't need this requirement in the proposition here that the information sets contain the earlier outcomes. There aren't any outcomes for this analysis here. So now sequence of forecasts for a single outcome Y, nested information sets. Remember, this was our definition of the revision function. We define the synthetic pit values in this way. So we have a uniform random variable U. We take Fj inverse of U and then apply Fi to that. So these are the synthetic pit values. And yeah, here's the statement of the result. So if this sequence of forecasts are efficient, then these synthetic pit values are uniform, and if the revision periods don't overlap, they're also independent. How to interpret these synthetic pit values? Well, one way to think about it is that Fj inverse of U is like a draw from Fj. And we can think of that as like a sort of synthetic observation for the time corresponding, or for a time where observations are generated according to Fj. So Fj is in the future, Fi is made before Fj. So we create a synthetic observation from Fj, and then if we think about Fi as being a forecast for that synthetic observation Fj inverse of U, then this is basically the corresponding pit value. It's Fi applied to the synthetic observation Fj inverse U. So, yeah, this is another way of thinking about this result that we have. So, yeah, that's what we have so far on revisions of probability forecasts and their properties. Here's a summary of what I've been saying. So, an interesting way of thinking about or analyzing calibration of forecasts is to look at forecast revisions. And if the forecasts are efficient, then their revisions behave in nice ways. Certain expectations, no correlation, that sort of thing. Yeah, we can define revisions of point forecasts and now also of probability forecasts. And this means that we can assess the efficiency not only of forecast means, but also of everything about forecast distribution, so by looking at these revisions. And as I said before, Tom's poster has more detailed theory. I wasn't sure how long this was going to take. See, it's taken 40 minutes. I added in a couple of extra slides on topics that I thought people might be interested in. So I think I'll take 5 or so minutes to just mention these other things, and then I'll be very glad to take questions on any of these things. So yeah, I had some previous and ongoing work relating to scoring rules, which have been discussed a lot. So I thought I would just mention these. Oh, here are some references that I've cited so far. Oh, the other thing I should have acknowledged. So someone else who was responsible for getting me interested in these revisions was James Mitchell, who used to be at Warwick Business School and is now at the Federal Reserve Bank in Cleveland. And he had thought about how to extend forecast revisions from point forecasts to probability forecasts before. So we had some discussion about that based around this working paper, which I'm not sure is available. You have to contact him for it. Okay, proper scoring rules. A couple of things I just wanted to mention. So one problem with proper scoring rules can be that, well, maybe we're trying to predict X. Different notation now, sorry. So X is what we want to predict, but maybe we never learn X exactly. So we only get some noisy measurement of X, which we'll call Y here. Then here's our probability forecast F, and this is a forecast for X. So maybe X is the real temperature in Cambridge on Saturday, but we only ever get some measurement of that, and maybe there's some error. Let S be a proper scoring rule. And here's an example to illustrate what sort of problem this measurement error can have. So suppose the true X comes from this normal distribution. Suppose there's some measurement error, so that Y is X plus some additive, so plus some normal noise with variance C squared. Suppose our forecast is normal 0 sigma squared. So the optimal forecast here would have sigma equals 1. And let's consider the logarithmic scoring rule, which is minus log of the forecast density evaluated at Y. So this is what we would normally calculate when we compute the scores of our forecasts. We would take the score of our forecast and the measured outcome Y. But if Y has got some measurement error in it, then maybe this is going to give us a misleading impression of how good our forecast is. And this diagram illustrates this problem. So on the horizontal axis is sigma. These are different forecasts that we might have made. On the vertical axis is the expected score. If there is no observation error, C equals 0. That's the solid line. This is how the expected score varies with sigma. And we see that it is optimized, minimized, when sigma equals 1, which is the true distribution of X. However, if there is some observation error, measurement error, for example, if c squared equals 0.5, then the expected score follows this dashed line, and we see two problems. One is that the score is biased, so the score is too big. It's indicating the forecast is worse than we thought, than it really is. The score is too high. But also the score is optimized at sigma greater than 1. So it's preferring an over-dispersed forecast relative to the truth. And if the observation error increases, those problems magnify. You can sometimes avoid this by using error-corrected proper scoring rules, which I discuss in this paper here. And Harris, who's also doing his PhD with me, has a poster outside that hopefully some of you saw earlier, extending these ideas somewhat. But yeah, the idea of these error-corrected proper scoring rules is that instead of using S as your score, you use this thing SC, which is defined in this way. So it's the score such that the expected score, when you plug in the noisy outcome, should equal the score that you would get if you knew the true outcome X. And sometimes you can find these corrected scores, not always. You're solving an integral equation to get this thing. But yeah, so that's one other thing that people might be interested in, and please do speak to Harris if you would like to know more about that. And then another thing that has come up a little bit is where you don't know the forecast distribution F perfectly, maybe you have only a sample from the forecast distribution. Weather forecasters would call this an ensemble forecast. So here the situation is we've got the outcome Y, this time assume no measurement error here. Probability forecast F is unknown. Instead, we've just got a sample from F. A sample of size M. And suppose we had a proper scoring rule S again. Then one way that we might think of scoring the forecast is to find the empirical distribution of the ensemble. That would be an estimate of F. I'll call that Fm. Then if we evaluate the score, putting in Fm here and the outcome Y, and then ask about the expected score, well, this expected score is not optimized when our ensemble is drawn from the true F, the true distribution. It's optimized when the ensemble is drawn from a different distribution. And we might prefer it if our scores were preferring forecasting systems that drew their ensembles from the correct distribution. Here's an example of, again, what can go wrong. Suppose we're forecasting a binary outcome. Maybe y equals 0 is that there's no hurricane, y equals 1 is that there's a hurricane. Suppose we've got an ensemble of ones and zeros. Then x bar, the mean of the x's, is the proportion of ensemble members that forecast the event y equals 1. So it's sort of a probability forecast for the event happening, or at least an estimate of that probability forecast. You might then plug this ensemble empirical distribution into the Breyer score. But if you do that, then you, again, can be misled. So if your ensemble size is 50, which is quite common for weather forecasts, and suppose the true probability of the event happening is 1%, so it's quite a rare event, but your Breyer score in expectation will be optimized when your ensemble never predicts the event. So your best ensemble to minimize your Breyer score will never predict the event happening. So if you just plug in the empirical distribution function, you can start favoring biased forecasting systems. But again, you can get around this by using what I call fair scoring rules. So again, instead of using S of Fm and Y, you change the scoring rule so that this property that we want holds, this sort of properness property holds. Here I should say the expectation is over both Y and the randomness involved in the estimation of Fm. And here's the fair version of the Breyer score. It's just a bias correction for the finite ensemble size. And you can read about that in that paper there. But yeah, these things are used quite in a few places now for checking weather forecasts. So they avoid this bias. Right, sorry, I've gone on long enough now. Sorry for fitting in all those different topics, but I hope that was interesting. And very happy to take questions now.
So we have time for questions? Yes, Tom.
Thank you, Chris. That was very nice. There's one thing about the efficiency concept that I find confusing. So what if at some point in your series you observe new information that is contradictory to the previous information, so it changes the expectation? Say the hurricane is not hitting Florida, and then all of a sudden it is. Does that mean the series is not sufficient?
No. So, yeah, the new information that comes along may well, I mean, okay. So when you say the new information is contradictory, maybe, so some information that you have in the past is shown to be false. Okay, yeah. So I suppose ideally we need to be taking into account the chance that this information we have could be false. So maybe we would need to know about that. And if we don't allow for that, then yeah, I guess we're not going to be able to satisfy this efficiency thing, because yeah, the true distribution of Y given that information will know that that's false information, or at least that's a possibility, and so our forecast will not match that. Yeah. So we need to be fact checking and being. Does that answer your point?
Well, so the information set can be like other forecasts, right? That alter themselves.
Yeah.
Yeah, I may have a question about slide 23. Yeah, so you have the ensemble forecast. So the thing is that there is a problem because the probability of having x equal to 1, so you may never observe one of the possible outcome. No?
You never observed in your ensemble forecast.
And so why not take this thing about this Laplace sunrising problem, for instance, where why not artificially add in the ensemble one x equal to 0 and one x equal to 1, such that now I think we do some kind of same thing for the isogenic regression for the path algorithm, because on the border you may also have issues. But if you kind of artificially incorporate a 0 and a 1, I was wondering if it may solve this kind of issue.
Right, okay, so maybe as forecasters we should always admit there's a possibility that the event could or could not happen. We should make sure that our ensemble covers those possibilities by putting in a 0 and a 1 at least, one of each. So the way that weather forecasting centers say that their ensemble should be interpreted, this is not how they're generated typically, but this is how they suggest they should be interpreted, as simple random samples from some distribution. I suppose if we are putting in these extra 1s or 0s, then maybe we would have to modify the guidance on the interpretation there. I don't know how the analysis would change there, but yeah, maybe you'd end up having to use a slightly different adjusted scoring rule if your system included those 0s and 1s. Yeah.
Yes, thank you very much for the very clear talk. I have a question continuing the question of Claude. So, if we think about extreme events, okay, and if you say at some point that when you define the efficiency with the expectation, yeah, and you only use this inclusion for information. If you go a bit more precise about the random variable, let's say, that represent information, can you take care of extreme information that we wish to take into account and that we wish to have maybe jump, okay, because of this extreme information? And does it rely to revise the notion of efficiency by looking at median or
would it be useful to refer back to the point forecast? That be simpler.
Sorry,
that would be simpler.
First part.
Okay. So I'm not sure I understood your question, so let me see. So if we are concerned about forecasts for extreme events, maybe we don't want our point forecast to be the mean.
Yeah.
We might want it to be some high quantile or something else. Is it? And then how could things, what analysis could be done then? Yeah, okay, so yeah, if the point forecast is an identifiable functional, then it can be defined with an identification function v, so a quantile or an expectile. There would be a v function, and we could define efficiency in this way. However, defining a revision in this case, so here is a very simple definition of revision. Tom thought about this, and he can correct me if I misremember, but one thing that you might think of doing is defining the revision to be the difference in the identification functions for the x1 and x2. The problem there is that that difference in the identification functions will usually still involve y. So the revision will depend on the outcome, and we don't really want the revision to depend on the outcome. So I think we don't know how to do this for things like quantiles. Tom's giving me a small nod. So
the only thing I'm thinking is if you think of an extreme event as, say, enough rainfall to cause a river to flood or something, you could focus simply on the observation being the variable being whether it floods or not, if you see what I mean, like whether the event occurs, and then the probability forecast would essentially just be your probability that you assign to the event that you get a flood. And then those values, being your forecasts, would form a martingale, and you can test that way. But if it's, yeah, I don't have anything to add to what Chris was saying, but if you consider the point forecasts, which are, say, the 99th percentile of your probability distribution, I don't know what to do with that.
I had a question. So you motivated this whole thing from weather forecasting. So in what sense does it extend, or is it necessary to extend the theory to not nested information sets? Because usually the data is so huge and vast that you have to have some horizon of what you actually take into account.
So I haven't thought about that until this moment.
Yeah. Blend it out in some sense,
but then you'd have to have the algorithm would have to do that as well. I mean, that
it's sort of less and less used.
So
I mean, at least for your theory, at least.
so you're thinking the case where older information is forgotten.
Yeah.
Yeah. It's not clear to me whether anything would be possible there. But okay, so maybe one could construct sort of example situation where the information is forgotten in a particular way, and but yeah, nothing occurs to me at the moment. That's an interesting question for sure.
Actually, well, so on your additional topic, I think it was like slide 22 or something. Yes, so here I guess the natural thing that I guess people do is simply to compute the distribution of the noisy forecasts. Right, you add the measurements to your forecasts. Why not? Why do this instead?
Right, yeah, thank you for asking, yeah. So you can just add the noise into the forecast, and so this was first done, as far as I know, by Anderson for rank histograms in assessing weather forecasts, and also this was the scoring rule corresponding to doing that was proposed by Jochen Brocker and Lenny Smith in a paper. If you do that, you make the scoring rule proper, so that's good. However, it is still biased, typically. So the curves then would all be minimized. These three curves would all be minimized at sigma equals 1, but the dashed lines would still be biased. So if you're concerned about avoiding that bias, then you might want to try this instead, which solves both problems. If you're only concerned about propriety, then taking that approach is a lot easier in some sense, in that you can always do it, whereas you can't always do this. Having this bias, though, as Harris illustrates on his poster, it can cause a real problem when you're doing hypothesis tests to compare two forecasters. The test will also be biased, typically, and it can give very misleading results.
Okay, let's thank the speaker again.